An inductor is a device consisting of a coil of wire wrapped around a magnetic material. A capacitor is a device containing two metal plates. If we connect an inductor and a capacitor together in a circuit, the current and voltage can oscillate as shown. We call the frequency of these oscillations the resonating frequency of this circuit. This frequency is determined by the value of the inductor's inductance and by the value of the capacitor's capacitance. The amplitude of the oscillations will gradually decrease due to the resistance of the wires. If the wires in this circuit hypothetically had no resistance, then these oscillations would continue forever. On the other hand, suppose that our circuit consisted of just a capacitor and a resistor. Once the capacitor discharges, the voltage across the resistor will be zero. Once the voltage across the resistor is zero, no current will flow through it. If no current is flowing, the capacitor will never recharge. But, unlike resistors, an inductor is a device which tries to prevent any changes to the amount of current flowing through it. If the current tries to stop flowing, the inductor will exert a force to keep the current going. In the circuit with the resistor, when the capacitor fully discharges, the current drops to zero. If we replace the resistor with an inductor, then when the current tries to decrease, the inductor will exert a force to keep the current flowing. This current will then charge the capacitor in the opposite direction. The capacitor will then want to discharge, and the cycle will repeat itself. Suppose that next to this circuit, we have an AC voltage source that has the exact same frequency as these oscillations. If we add a resistor as shown, the voltage at both sides of the resistor will always be equal. This means that the voltage drop across this resistor is always zero. If the voltage drop across a resistor is always zero, then no current will ever flow through it. From the perspective of the AC voltage source, the inductor and capacitor parallel combination behaves like an open circuit. The inductor-capacitor parallel combination can be replaced with an open circuit, and the AC voltage source wouldn't know the difference because no current would flow through the AC voltage source in either case. Now, suppose we take the same inductor and capacitor we had before, and we connect them in series, instead of in parallel. Since all the components in this circuit are now connected in series, every point in this circuit will have the exact same amount of current passing through it. The resonating frequency of the inductor-capacitor combination is still exactly the same as before. With the components connected in series instead of in parallel, the inductor-capacitor combination acts like a short circuit instead of like an open circuit. This inductor and capacitor in series could be replaced with a short circuit, and the AC voltage source wouldn't know the difference, because the exact same amount of current would be flowing through the AC voltage source as before. However, this is only true if the frequency of the voltage source is exactly equal to the resonating frequency. The closer the frequency of the voltage source is to the resonating frequency, the more the inductor-capacitor series combination will look like a short circuit, and the larger the amplitude of the current will be. The opposite is the case if the inductor and capacitor are connected in parallel. The closer the frequency of the voltage source is to the resonating frequency, the more the inductor-capacitor parallel combination will look like an open circuit, and the lower the current through the voltage source will be. Details about inductors are available in the video titled